Hello, howdy, I'm Mr. Stark, and welcome to the first lesson on limits. There are 8 total lessons in the unit. In this lesson, we'll learn about average and instantaneous speed, the numerical understanding of limits, the limit definition, the graphical understanding of limits, and the algebraic properties of limits. Since this video is longer than usual, I encourage you to use the video chapters to skip around if needed. Let's get started. While the title of this lesson is Definition of a Limit, we're going to start with average and instantaneous speed because they help us understand the concept of a limit and what it's used for. Let's start with a position function. S of t equals 16t squared. T represents time and S represents position based on time. But S really stands for spatium, which means space or distance in Latin. Great, we have a position function. So how do we find average speed? Well, that makes me wonder, what is speed to begin with? Speed is the magnitude of velocity. So speed gives us the intensity of the velocity without direction. But I want to make sure that you know that average velocity and average speed are just contextual applications of average rate of change, or slope. And I want to be clear what I mean about contextual application. So here's what I mean. When we're talking about functions, the contextual application of functions are position functions or velocity functions, or any functions that take that mathy thing and put it in the real world. For the mathy concepts of slope or average rate of change, examples of contextual applications for those are average speed and average velocity. If I wanted you to calculate the average speed from time equals 0 to time equals 4 of this position function, then you would use the slope between 2 points. If you like, you could find those 2 points and the slope in between those 2 points. Our focus together, however, is how to calculate instantaneous speed at 1 point. We do that by using the limit of the difference quotient, the limit as h approaches 0 of f of t plus h minus f of t divided by h. In the numerator, we have the difference in the distances, and in the denominator, we have the difference of the time values. In other words, h equals the change in time, and eventually that change in time is going to approach 0, but not officially be 0. Let's find the instantaneous speed at time equals 4 then. We'll start by plugging in 4 for t so that we get the limit as h approaches 0 of 16 times 4 plus h squared, that 16 is in the original position function, minus 16 times 4 squared all over h. Since those parentheses in the original formula are function notation, that means 4 plus h is being plugged into the function, just like 4 is being plugged into the function. That yields the limit as h approaches 0 of 16 times 16 plus 8h plus h squared, which is that 4 plus h binomial expanded. Many students forget that 8h, minus 256 divided by h. If you're following along using the guided notes, you might be running out of space, so just write smaller. We have 2 main steps left. Distributing that 16 gives us the limit as h approaches 0 of 128h plus 16h squared divided by h. Notice that the 256's subtracted out, and now we have an expression that if we plugged in 0 for h, we would get 0 plus 0 divided by 0. That doesn't make sense. 0 divided by 0? What is that? Is it 1? Because any number divided by itself is 1? Is it 0? Because 0 divided by any number is 0? Or is it undefined? Because any number divided by 0 is undefined. That is exactly why we're letting h approach 0 and not become 0. Stick with me here, and let's factor out an h from the numerator so that we get the limit as h approaches 0 of 128 plus 16h. What happened? Well, that h in the numerator divided with the h in the denominator. Using the formula for slope and a limit allows us to use algebra to eliminate the issue, that divided by 0 issue that we had in the last step. Notice that we can easily plug in 0 for h now, so that we get 128 plus 16 times 0, which is just 128. I know, I said that we were going to let h approach 0 and not become 0. But what we were really doing was allowing h to be a placeholder for 0 until we could eliminate any issues that came about from plugging in 0 originally. Don't miss what happened, by the way, that when we plug in 0 for the expression that we're taking the limit of, that limit goes away. We've evaluated that expression using the limit. The result is 128. That's the instantaneous speed at time equals 4. The units for that would be something like feet per second. And we can actually say that this is the instantaneous velocity as well, because the position function, 16t squared, is always positive. So that means velocity and speed will always be the same value. In conclusion, to find average rate of change, average velocity, or average speed, you're finding 2 points and you're just using slope. To find the instantaneous rate of change, instantaneous velocity, instantaneous speed, or we'll look at other contextual situations later, we use the limit of the difference quotient. Now that we've covered average and instantaneous speed, it's time to switch gears. Let's kick it into numerical. Get it? Kind of sounds like neutral, but it's numerical. We'll be using this table and we'll fill in the values as we go. These values give us a lot of information about the function, so that's why we start with the numerical understanding of a limit first. Then we'll move into the graphical method or approach, and finally the algebraic. For the numerical approach, I'll use a TI-84 graphing calculator, so if you have one, follow along. We are on the main screen of the TI-84 graphing calculator. Let's just make sure you have the right settings. Click on mode, and we're in function mode. The first 8 or 9 settings should be highlighted on the far left, but function is really the main thing. Then second mode to quit, and then we'll go to the bottom of the screen. You can see my key press history, so if you lose track, you can always pause and see what I actually pressed to get there. So in the y equals menu, we're going to enter the first function, and it's a fraction, so let's use the alpha y equals shortcut and choose option 1. This rational function is x squared minus x minus 2 divided by x minus 2. At the end of that first 2, you press the right arrow to get into the denominator. I'll let you enter that, and just a note that we're expecting the limit of this function to be 3 when x equals 2. And we can see in the denominator that there's an issue when x is 2. So we'll go to second graph, which is the table menu. You'll see that your values might be different than mine, and that doesn't matter. We're just going to reset those right now, but you will see on my screen that there's an error at x equals 2. So let's go to second window to the table set and mess around with those settings. We want the table start to be 2 because that's where x is approaching, and the delta table, just let's start with 1 for now. We're going to make it smaller later. The other features should be set on auto. So let's hit second graph to go back to the table. And you should have x equals 2 at the top left of your table. And just press the up arrow to see some negative values. So this is showing us that the function is undefined at x equals 2. There's an error. And at x equals 1, the value is 2. X equals 3, it's 4. So you could see that in between 2 and 4, we're expecting that the limit, or we expected that the function value should be 3, but there's an error. We should be comfortable with the fact that y is approaching 3 when x is approaching 2, but let's zoom in a little closer. Second window takes us back to our table. We have to change the table start because we moved around the table. And let's make the delta table 0.1. So x is going up and down by 0.1. Back to the table allows us to see that the x values go up by 0.1 and down by 0.1. Notice the error is still there, but we're a little closer. And if you're following along with the notes, you could enter the values for 1.8 and 1.9, the y values. You could also enter the values for 2.1 and 2.2. So notice that the value in between 2.9 and 3.1, we're expecting it to be 3.0. So not really surprised by that fact, because it really completes that pattern. And there's still that error there. That error is telling us that the function is undefined at x equals 2. There's no y value that corresponds to x equals 2. But the values around that, 2.8, 2.9, 3.1, 3.2, are showing us that the y value is approaching 3. Just for giggles, let's zoom in a bit more and change the settings for delta table to 0.01. So we're letting x go up and down in a smaller increment. Second graph takes us back to the table. Arrow up a bit so we could see the x values to the left of 2. So on the graph, they would be to the left of 2. And I want you to record the y values for 1.99 and 2.01. They just show you that the y value is not doing anything different than we expected it to do. So the y value that corresponds to 2, we're expecting it to be 3.0 still, or 3.00 if it's down to the 100th value. Taking a numerical approach to limits and mastering these table settings allows you to collect a lot of information about a function. We were able to identify that this function was undefined at x equals 2 because of the error. We were also able to zoom in closer and closer to x equals 2, kind of like we would with a graph, but with numbers. You know, working with integers, then working with decimals, and even smaller decimals. Finally, we were able to see that y approaches the same number when x is smaller than 2 and when x is larger than 2. That's it for numerical limits for now. Remember to use this method first when you're allowed to use your graphing calculator. So far, we've calculated instantaneous speed using a limit, and we've found the limit of a function numerically. Now what I want you to try to do is to create a definition of a limit from your numerical observations. I want you to pause the video and ask yourself, what is a limit? Here are some questions to guide you. Is a limit like a function in that it depends on the x value? If a function is undefined, can a limit be defined? Finally, how can you use x values and y values to describe what a limit is? Okay, pause now if you haven't already. Before I share a semi-formal definition of a limit with you, I want to describe my own personal observations from the two examples that we worked through. From the first example, I observed that a limit allowed us to shrink the time interval that we were using to calculate slope. Based on that, I would define a limit as a number that the calculation was approaching, a number that the slope was approaching, or the speed. In the second example, I observed that I had this expectation as to what f of 2 was supposed to be. It was supposed to be 3. I could see it in the table. From that, I would define a limit as a number or an output that I expect a function to be or approach. And whether you wrote it down or not, maybe your definition was pretty close to what I just mentioned. Okay. Here's that semi-formal definition. The limit as x approaches a of f of x means f of x gets arbitrarily close to L, the limit, as x gets arbitrarily close to a. As x approaches a, starts to become a, gets closer to a, f of x approaches L or becomes L. Arbitrarily means that x is not approaching a in a very specific way, as in x is not increasing by 1 every time or 0.1 or whatever. It's that If x needs to increase by a smaller and smaller value as x approaches a or gets close to a, then so be it. There's a more formal definition in calculus textbooks, and you could also find it online. I encourage you to check it out. The next thing we'll do is calculate limits graphically. When finding the limit of a function, it's best to start with the numerical approach, like we did, then move on to the graphical approach. We'll check out the algebraic approach in the next lesson. If you have a TI-84 calculator, I recommend following along. Okay, here we are on the main screen of the TI-84. Let's go to y equals, and I have the original function we worked with earlier in y1, and I have a new function that has a cube and a square, 8 and 4. So I'm expecting something to happen with x equals 2 or negative 2. You can pause and enter y2 now, but we're going to go to zoom 6 so we can see the graph of both of these. One ends up being a line, one ends up being a curve. And really what I want to do is only look at one function at a time. So let's go to y1 and turn off y2 by hovering over the equal sign and pressing enter. Now we only see y1. And so I just want to point out, you remember earlier that there was an issue at x equals 2. And so if we trace the function, we could go near x equals 2 and see what's going on. So we're approaching 2 from the left side. And we see that x is getting so close to 2, y is getting very close to 3. But I don't actually see any issues. So we go on the right side, and we get closer to 2 from the right side. And y is getting closer to 3. So this is just a simple graphical approach. We're using the trace feature to see what's going on. I just pressed second trace so we could enter a value, and I'm entering x equals 2 so that we could see what the value of the function is at x equals 2. You can see that y doesn't have a value. It's not defined. It's undefined. So the value of the function is not defined at x equals 2, but we just saw that y approaches 3 as x approaches 2. And that was in an arbitrary way. You know, we just moved closer and closer to x equals 2, and we saw that x was approaching 3. We could look at the table again just to verify what we see in the graph. So this is kind of synthesizing both the table and the graph, the numerical approach and the graphical approach. And so now let's turn off y1 and go to turn on y2 by pressing enter on the equal sign. And we could just press graph this time. We don't have to do zoom 6. It already has a standard window. And you might notice something's going on at x equals negative 2. That looks like an asymptote to me. So we're not really interested in that because we're approaching x equals 2, not negative 2. But you know, we could analyze that graphically as well. We move from the left and the right side of x equals 2 to see that there's no value at x equals 2 for y. And then we're approaching positive 2 from the left side, and we could see that y is approaching 3. We could approach x equals 2 from the right side, so something greater than 2, getting closer and closer to just 2. And we can see that the y value is approaching 3. So this is a very basic graphical approach to the limit. We're just trying to get a feel for what the value of the function is supposed to be or what we expect it to be. Again, we could look at the table, so second graph, and we could see that at x equals 2 there's an error, but it doesn't show up on the graph. And that's the problem with the graphical approach. Is the TI-84 is really not fancy enough to show us, hey, there's a hole at this value, at this. Finally, here are some algebraic properties of limits. The properties are included in calculus textbooks. They're also searchable online, and I discuss them in a little more detail in my Intro to Calc playlist, topic 3. Also, these properties don't represent the algebraic approach or method in finding limits. Those methods are methods that were presented in Algebra 2 or Pre-Calc, and we'll discuss those in the next lesson. Last thought, notice on the top left, if the limit as x approaches c of f of x and the limit as x approaches c of g of x both exist, then all these properties are true. And they're true because each limit expression represents a real number. which is why all the properties reflect the properties of real numbers.